welcome back to this Red Door Analytics online course, Survival Analysis, and Introduction to Concepts, Methods and Software. In this section, we're going to talk about censoring. So we've discussed that the event of interest is one of the key aspects of survival analysis, along with time. However, we may not know if or when individuals had an event of interest. When this happens, we say that an individual was censored. There are three types of censoring to note. There is right censoring, and here this is our focus since it is the most common type of censoring. There's also left censoring and interval censoring. So let's focus on right censoring to begin with. So when we stop following an individual and they have not had the event of interest, then we say that an individual has been censored or right censored. So here on our timeline, we see that we have breast cancer diagnosis on the left. We follow these individuals across their years since diagnosis. And at this blue dashed line, we see that we have an end of study, at which point we haven't observed any death. Because if you can see on the grey part, we actually see that these individuals do die later than the end of our study. But during our study period, we wouldn't be able to know that they died later or when they died later. So at this time point at the end of the study, they would be censored because we know that they did not have the event of interest or they did not die during the study period. They would be censored at this time point. So there are many reasons why an individual may be censored. For instance, the end of a study period, as shown here, they could migrate from the country, so we no longer have information on them. Or they could experience a competing event. For example, if we're looking at death, or if we're looking at another outcome other than death, and they die prior to getting the event of interest, then we would censor them at their death. So as I said, right censoring is the most common type of censoring. There are other types of censoring. Left censoring is one, and this occurs when the event of interest has already occurred prior to study entry, and the time at which the event occurred is unknown. This is not as common as right censoring, and typically when we refer to censoring, we are referring to right censoring. There's also something called interval censoring, which occurs when we know that the event occurred within a range, but we're not entirely sure when. So for example, suppose we have a screening study. So we have individuals here on the y-axis and we follow them. Here now we're looking at months since a study entry. And at the blue vertical lines, we screen individuals to see if they had the event of interest at that time point. So the first individual, we follow them across our months since study entry, and at 6 months we screen them and we do not see any event of interest, and we keep following them until we see that they do have the event of interest at the second screening. If we look at the third individual here, we see that we follow them across time, at which point at the first screening at 6 months, they have the event of interest, then we stop following them. And you can see this differs for different individuals here. But if we look at these two individuals of particular interest here, the two that are represented by red here, where we see that this first individual, the first red individual, actually has an event of interest at the first screening, and the second red individual has an event at the second screening, then is this really what happens? Well, no, actually in these two individuals, they actually had the event of interest at a time prior to screening, but we didn't detect it because of the screening program. So this is actually the time at which they had the event of interest at around 3 months for the first red individual, but we would only detect it at screening at 6 months. So this is what we mean when we say we have interval censoring, that the event happened within a range, but we're not entirely sure when. For this individual, we would not know that this happened at around 3 months. We would just know that at 6 months, they had the event of interest. Okay, but let's go back to censoring in terms of right censoring here. And why is this so important? Well, we need to censor to ensure that our time at risk is correct. Later, I will show you an example of calculating the crude rate of an event when using the correct versus the incorrect person time at risk, which is related to our censoring. So you should be able to see later on when we talk about rates why this is really important. But for now, if we look at this figure here, where again we have individuals represented on the y-axis, and we follow for a study period of 20 years since breast cancer diagnosis, and the event of interest is death, then we can see that we have these different lengths of lines of individuals. Now, if we didn't censor these individuals, then we would just continue following them for this dashed period of time. So the first individual where we actually followed them for around 5 years, at which point they are censored, we would actually follow them for a total of 20 years instead. So you could see that the time at risk would be very different if we ignored the censoring. So there's one important concept when it comes to censoring in survival analysis, and that is non-informative censoring. So this is a concept to consider when performing survival analysis, and it's whether censoring events are informative or not, i.e., is the distribution of survival times independent of the censoring times? So one way to think about this is to think about what would be informative censoring. But patients should drop out of the study for reasons unrelated to the study to avoid bias. So one example of informative censoring would be that patients on a certain treatment drop out of a study due to side effects related to that treatment. So there would be a reason why we are censoring them that's related to the treatment under study. This can cause bias. Note that there's another term, independent censoring, which is a separate but related term, which is used when the non-censored observations in a subgroup of the study are representative of those in the subgroup who have not been censored. If you want to read a bit more about this, you can in the reference here. So what do we do if we think that censoring is informative? Well, there are no statistical tests to see whether censoring is informative or not. You have to use the knowledge of the subject area to determine whether it is likely or not. If you do decide that censoring is likely to be informative, then the following methods could be useful. You could look into competing risks analysis, inverse probability of censoring weightings, or imputation methods. There's some references here if you'd like to read more about them. These are more advanced topics, so we won't be covering them in this course. So one question you may be asking at this time point is, if we have an outcome of interest which is binary, why can't we just use a standard analysis approach? And by that I mean, why can't we use a logistic regression? Why do we have to have a separate survival analysis field? Well, we have to consider the time at risk and the issue of censoring in order to avoid biased results. And the survival analysis framework allows for this. There's other related concepts that you may be of interest in learning about, which we'll cover very briefly here. We have some references where you can read some more about these. One of which would be left truncation. And this is when individuals who experience the event prior to the study start are not included in the study. So individuals only enter the risk set once they have survived to a certain amount of time. This is a type of sampling bias that should be considered when interpreting results. Another related concept is immortal time bias. This is definitely something that you should avoid and be aware of. Is a problem that occurs when defining the exposure based on future time points that can distort the exposure outcome association. So for example, if you're interested in comparing two different treatments, and at the time of study start, you have individuals on treatment and some patients who are not on treatment. As you follow across the study, some individuals change to become on treatment. Well, then you should not put those individuals into the treated group at baseline. They should be treated as though they are untreated and then switch to treatment at the time point at which they switch. Otherwise, you may have problems and get biased results. Another thing to think about is delayed entry. This is when individuals or observations contribute to time at risk from a time point after the start of study or origin of the timescale. This can be dependent on the timescale. And time at risk contributions should be adjusted to account for delayed entry. So here you can think about attained age timescale. We can see that individuals contribute on this timescale at different time points. So we don't follow everyone from the same time on this timescale. For example, the first individual, we start following them from around 57 years, and the second individual from around 60 years. So you can see that this is shifted across this timescale. Here's some further reading around these topics, if you're interested. If not, I will see you in the next section.